So we can go back to a little bit of kinetics actually, and we can build ourselves a model. And so we can kind of write the chemical species, I suppose. So S represents the grain state molecule. I'm going to go ahead and write S star is going to represent sort of the S1 excited state. And I'm going to go ahead and represent T star as an excited triplet state. And I can imagine conversions between one and the other. So we can go from S to S star through absorption. We can go back from S star to S through fluorescence, and we can give it a rate constant K sub F. We can go from S star to S through internal conversion. So internal conversion is this process where we have a non-radiative transition. So essentially the molecule, instead of kicking off photons, it basically dumps that energy into surrounding solvent molecules. And so actually, depending on the solvent you dissolve your substance in, you might see significant amount of fluorescence, or you might see a quenched situation where there's really no fluorescence at all. So that that internal conversion there is that non-radiative transition. And we can go from S star to T star, so we can go from that first excited singlet state to that lowest energy triplet state through intersystem crossing. So that's another possibility. So ISC, and we can give that a rate constant K sub ISC. And I don't think we really need this, but you can also go, of course, from that triplet state back to the grain state through a process called phosphorescence. But we're going to focus our attention on the decay of this singlet excited state. So we really don't have to worry about this last transition here, since it doesn't directly affect the loss of S star. We can go ahead and write rate laws for all these processes. So if we're just looking at S star, then there's only one possibility to make it, and that is absorption of light. So we're taking S, and we're taking a photon that is incident upon there, and it's turning it into that S star excited state. And we're going to say that the rate of that is directly equal to the rate of the absorption, so the intensity of the absorbed light. Okay, and then we've got fluorescence that acts as a way to deplete S star, and so S star reconverts back into S, and it gives off that photon, that final fluorescence photon, and it's going to have a rate equal to that rate constant Kf times by the concentration of S star. We've also got intersystem crossing, so the ability to take S star into T star, and so we're crossing between those singlet to triplet states, that spin forbidden process, and the rate of that we're going to say is equal to K intersystem crossing times by S star. And then we've also got the internal conversion, so that non-radiative transition. So basically we return back down again, and instead of releasing a photon of light, that energy gets dumped into surrounding solvent molecules, and that rate is going to be K internal conversion times by S star. So we've built ourselves a model. So remember, all models are wrong, but some are useful. So we're just going to go ahead and study and see what happens to this excited state within this model right here. What we're going to do here to simplify things is we're going to look at the concentration of S star immediately after we turn off the light. So immediately after we shut off the incident light. So we don't have to worry then about what happens, right? So we've got the excited state decaying, and as long as we shut off the excitation light, right, we're not going to be creating more of this excited state. So within this model then, we can go ahead and write down an equation for the rate of decay of S star. So S star, right, we know it's going to decrease, so we're going to put the negative sign there just to remind ourselves that that concentration is going to be decreasing. And we might as well keep the negative sign to the left-hand side rather than write it 3 or 4 times on the right-hand side. So we've got the kinetics above, so we can go ahead now, and of course we can ignore this process here because we've turned off the incident light, so there's no more S star being created. But we've got fluorescence that's depleting that concentration, we've got intersystem crossing, and we've got internal conversion. So we can go ahead and write those rate laws there. So we can say that the fluorescence is depleting by a fluorescence rate constant times by the concentration of S star, and we're also depleting thanks to intersystem crossing. So we can go ahead and write this term here, and then we've got the internal conversion depleting it as well. So we can go ahead and we can write that, and you can see that we can actually factor out all those rate constants. So it's K fluorescence plus K intersystem crossing plus K internal conversion, all multiplied by the concentration of that excited state. Now, if we look at this equation here, we recognize this is really just a first order decay process here, and we've got a composite rate constant. So instead of a single rate constant here, we've just got a sum of them, but we've already solved these back in the first semester. You just need to separate and integrate, so you can move the S star down there and the dt over there, and then you just basically you're integrating 1 over something d something, that's the natural log, and that's just k times by t. And if you anti-logarithm, you essentially get an exponential decay. So we can go ahead and we can do that then, and we can write the result of that. So S star at the time t is equal to S star at the initial time. So we've excited the molecules, right, and we've turned off the light, so now it's just decaying away, and it's an exponential decay function here. So it's exp, or e to the power of minus, and then that effective rate constant kf plus k intersystem crossing plus k internal conversion times by t. So we have ourselves a nice exponential decay, and we can rewrite that if we want to. So we can rewrite that as s of 0 times by e. So this is, I should have said, this is s of t is equal to s of 0 times by exp minus t over tau 0. Okay, and what is tau 0? Well, tau 0 is just 1 over kf plus k intersystem crossing plus k internal conversion. So we've really just played with our equation here, but this is a very common form actually to write these kind of exponential decay functions as, and we refer to this as a lifetime actually. So this is the observed lifetime, and there's lots of situations when we have exponential decay where we talk about lifetimes. So this is the observed lifetime of the singlet state. Okay, and so it's just a definition here, and we've got an exponential decay, so we should go ahead and take a look at what that exponential decay curve looks like, but maybe a reminder from some physics here. And so let's go to the next slide. And so back in physics, right, you probably studied this simple circuit here. We've got a battery with a particular voltage here, and we have a resistor and a capacitor in series here, and so the resistor has a resistance R and the capacitor has a capacitance C, and we often are interested in the amount of charge we can put on our capacitor. So we cook this situation up, this circuit up, and we know that electrons will flow, or actually current, I should say, flows from the positive to the negative end. The electrons actually flow the other way, and so we build up charge on the plates of the capacitor. And if we want to know how quickly we build up this charge, it's an exponential increase function actually, and I believe the formula looks something like this. So the charge on the capacitor is equal to the maximum charge times by 1 minus e to the minus t over tau. So it basically looks exactly like we've seen before. Tau here is given by RC, the resistance times the capacitance. And this curve here is basically 1 minus an exponential function. So it looks something like this. And we can see that this is Q max. And we're interested in tau because tau actually tells us the time it takes for 63% of the charge to build up. So this is 63% of Q max here. And so this is just one of those interesting factors here that we see over and over in exponential decay or exponential increase. And why 63%? 63% is basically equal to 1 over E. So after 1 unit of exponential growth, then it takes an amount of time given by RC. Our friends in biology sometimes talk about this as well. So it turns out that if you make the resistance or the capacitance smaller, you can decrease tau, so you can charge up much more rapidly. In fact, our nerve cells actually have a myelin sheath, a lipid layer, and what this does is it actually greatly reduces the resistance of our neurons. And if the resistance is much lower, then RC is much lower, and so it turns out that it charges up much more quickly. So if you're sending essentially electrical current down a wire or down some kind of molecular wire, then you want the wire itself to charge up very quickly and then allow the current to flow. And so the smaller this time constant is, the better and faster the signal goes on down the line. So since it's an exponential decay, we can go back to our fluorescence decay curve that we've predicted here. So this is time on this axis here, and this is the intensity of fluorescence. And again, it should be an exponential decay curve. So we start out, and we have that sharp decay that never quite gets down there. And of course, your data itself, right, that you would collect, I mean, your data is never going to be exactly on the line. We've got individual molecules fluorescent here, so we've got sort of a law of large statistics. But we can normally go ahead and we can fit this function. We can say that this can be fit to sort of something proportional to e to the minus time over tau situation, or tau sub 0. And so by fitting it right, then we can determine tau sub 0. And remember, tau sub 0 is just 1 over the rate of fluorescence plus the rate of intersystem crossing plus the rate of internal conversion. So experimentally, we can collect this data here, and we can find this tau function here, and we can relate it to the inverse of the sum of all these rate constants. So if tau is small, then we're going to have a small number in the denominator here, so it's going to make this a large and very negative value here. So that means that the curve is going to fall off very quickly. So if tau is large, if tau is small, right, it's going to generate a very large exponential term here, a very large negative term, and so it's going to lead to a rapid fall off here. And conversely, if tau is large, okay, so if tau sub 0 is large, if you're dividing by a large number, right, this is going to be a smaller negative quantity, so e to the minus a smaller quantity then is closer and closer to 1. And so what does this mean if tau is small? So if tau is small, then that means that the rate constants themselves must be pretty large. And so it makes sense, right? If all these guys were large here, we would be basically removing S sub 0 concentration, so it would be falling off very quickly. And if tau is large, that means that these rate constants here must be small, so we're seeing a small decay of our excited state. So it takes longer and longer for this curve to eventually bottom out. Not every molecule decays via fluorescence. In fact, it's typical to talk about the quantum yield, and so we can define a term here, the quantum yield of fluorescence. So we've seen that there's 3 avenues, right, for the excited state to go. It can either fluoresce, or it can intersystem cross, or it can internally convert. And so these two here don't release a fluorescence photon. So if we want to know the quantum yield, then we can basically go ahead and say that that is equal to the rate of fluorescence divided by the rate of photon absorption. And what this is actually doing is it's telling us essentially for every photon that comes in, what's the probability that it's going to come back out again as fluorescence. So imagine you had 100 photons come in, but you only had 80 photons go out via fluorescence. That means that 80 out of 100 times the molecule returned via fluorescence route, with the other 20 times it internally converted or it intersystem crossed. So basically it's just the ratio of photons out to photons in. So if something has a fluorescence yield of 1, that means that when you shine light on it, that thing lights up like crazy. So all those photons of fluorescence come out. When something's got a fluorescence yield, a quantum yield of fluorescence rather, of 0.01, it's telling you for every 100 photons you put in, only 1 is coming out as fluorescence. So the molecule is dumping and getting rid of its energy in another fashion.